Hi everyone, Dr. Burns here, and we are going to talk about our last topic in Chapter 6, which is Lewis structures and formal charge. Our new topic here is this formal charge word. We've learned about Lewis structures, how to draw them, how to follow the octet rule, as well as the exceptions to our octet rule. And what we found that if we follow those rules, we pretty much always get the same structure. However, we need to take formal charge into account for times when maybe you drew a Lewis structure and you look to your neighbors and they drew the Lewis structure just slightly different, but you each followed the octet rules and our exception rules exactly as we taught them. So the example that I like to show when we talk about this is the different structures that we could have for something like carbon dioxide. So maybe we have carbon, sometimes we show it as a double bond O on either side of those carbons. Okay, so that's our typical structure for carbon dioxide. My carbon has its 4 bonds, okay, which we also talked about that carbon likes to have 4 bonds. We also have our 2 oxygens where they have their 2 bonds and 2 lone pairs, which we know oxygen likes to follow those rules as well. But let's say you look to your partner and they had this drawn for carbon dioxide. Okay, so what's different about these structures? Well, my carbon still has its 4 bonds. They're just associated differently to those different oxygens. So one oxygen has 1 bond and 3 lone pairs, while the other oxygen has 3 bonds and 1 lone pair. Now, if I never told you about the elements that have specific numbers of bonds and lone pairs, you wouldn't say that either of these structures is wrong because they each follow the octet rule. I would have assigned my my electrons in the right way and everything like that. When I had to go to make double bonds or triple bonds, I could have just chose one oxygen instead of both, okay, in order to make this version rather than this one. Okay, both of these structures are technically correct because they follow the octet rule, and that's really up until now our only kind of guideline for drawing these structures. If I never told you that oxygen likes to bond twice and carbon likes to bond 4 times and each different element likes to have a certain number of lone pairs or no lone pairs, if you didn't know that, you would see no difference. So this is where formal charge comes in. Formal charge is going to be used to determine the most plausible Lewis structure when there's more than one possibility that exists for a specific compound. Essentially, what we want to do is look at the individual elements within that structure and decide which one is going to give the best formal charge. And in this case, the best formal charge is closest to 0. Okay, so that's either, exactly 0, minus, or plus 1. That's our preferred formal charges. And whatever the formal charges are of those individual elements, they should all add up to the formal charge of the specific compound itself. So if it's neutral, they should all equal to 0. If it has a 2 minus charge, they should all equal to 2 minus. Okay, and what really decides this as well is how electronegative different elements are. So we also have to refer to our electronegativity chart in order to determine how the formal charge is going to be distributed. And that's what we're going to learn about in this lesson. So formal charge is something we can calculate, and I know we said we're not going to do too many calculations in Chapter 6. Again, this is just some addition and subtraction like we've been doing. Don't worry, it's nothing too crazy. But our formal charge is calculated by doing the number of valence electrons minus the number of associated electrons. Now we find the formal charge for each individual element within our structure. Okay, so we're going to find this, if I were to use the example of carbon dioxide, for each oxygen as well as the carbon. So we would find 3 formal charges overall, 1 for each element. Okay, so the valence electrons would be for that specific element. So in this case, if I were to look at carbon, if I'm looking at this first structure of carbon, it has 4 valence electrons. And then we get to this associated electrons. The associated electrons is all of our non-bonding electrons, which we refer to as lone pairs. Okay, those would be considered associated, as well as half of the atom's bonding electrons, or their bonded pairs. Okay, those are associated with the atoms. We look specifically at the bonding atoms. We do the 1/2 because there's that sharing of the electrons. So half of these electrons came from the carbon, the other half came from the oxygen. Okay, so carbon really only claims those individual electrons that it contributed to the bonds being formed. Okay, so here's a more detailed kind of description of how we calculate those associated electrons more specifically. I do want to point out here that as you're writing these into your packets, you need to be showing all of this work. So that formal charge calculation, you need to be showing it for each of these individual elements. You can't just wait for me to say the answer and just put that number. I do need to see your work in order for this to be properly graded. Work needs to be shown in order to get full credit. Okay, so we're going to look at the example of ozone. So O3, ozone, and we want to calculate the different formal charges for each of these oxygens. So oxygen each, because there's 3, this one goes with this one goes with that one, and that one goes with that one. Okay, so each of them all have 6 valence electrons. We get that right off of the periodic table itself. Now we want to calculate the associated electrons. So let's look at this oxygen first. Okay, I'm going to write this in red pen to go with my red highlighted color. So, for the associated electrons, it is going to have 4 unshared. Okay, those are the non-bonding electrons. So that's going to be 1, 2, 3, 4. So we look at all of those lone pairs and we count the total number of electrons that are in them. So it's not the number of pairs, it's the number of electrons in those pairs. So here I have 1, 2, 3, 4. So those are my non-bonding or my unshared electrons. We're then going to add to that our bonding electrons. And remember, that's where we're going to take the half. So this oxygen has 2 bonds going to it. Okay, so it's a double bond. So within those double bonds, there's 1, 2, 3, 4 electrons. So there's 4 shared electrons between this oxygen and the oxygen next to it. Because this oxygen only claims half of those, we're going to take 4 and divide it by 2. So that simplifies to 2. So we have 4 unshared plus 2 that are shared. So we add those together and we get 6 associated electrons. So we come down here and our calculation for the formal charge is the valence electrons minus the associated electrons. So 6 minus 6. So 6 valence and those 6 associated that we just calculated. 6 minus 6 means that this oxygen has a formal charge of 0. Okay? Okay, let me erase this so we can change our color and see all these again. If you didn't get those, feel free to pause and go backwards. We're going to go to blue now. I just don't want to get too busy here. So let's look at this middle oxygen now. So it's still going to have the 6 valence. That doesn't change because that's coming from the periodic table. But now we want to calculate the associated electrons. So we first look at the unshared electrons. So that's the lone pairs. There's 1, 2 unshared electrons. So 2 electrons that are in lone pairs. So that's how we get our 2 unshared. Okay. We're going to add to that the total shared electrons divided by 2. So this oxygen has 1, 2, 3 bonds. 2 on one side, 1 on the other. So it has 1, 2, 3, 4, 5, 6 electrons associated through those bonds. So 6 electrons are being shared. But again, it only claims half. So we take that 6 and we divide it by 2. So we have 2 unshared plus 6 divided by 2. That's going to be 3. So that's going to give us 5 associated electrons. That's what we see down here. Now to calculate the formal charge, it's going to be 6 minus that 5. So our valence electrons minus the associated electrons. We calculated the associated electrons to be 5. So I'm going to do 6 minus 5. And that gives me a formal charge of plus 1. Okay, so the middle oxygen has a formal charge of +1. So even though they're both oxygens, they can have different formal charges because they have a different number of associated electrons with them. Okay, let's do our last oxygen. I'm going to go back to red for this one. So we're going to do this last oxygen here. We'll do this one kind of quickly now that we've done 2 examples so far. So it has 6 valence electrons. That comes from the periodic table. We now want to look to its associated. So we look first to the lone pairs. There's 1, 2, 3, 4, 5, 6 electrons in the lone pairs. So that's 6 unshared electrons. This oxygen has 1 bond to it. That 1 bond has 2 electrons, but it can only claim half. So I have 2 shared electrons and I divide that by 2. So I have 6 unshared electrons plus 1 shared electron through that bond. So that gives me 7 associated electrons. So if we use that to calculate our formal charge, I do 6 minus 7, valence minus associated, okay? And that's how I get a formal charge of -1. 6 minus 7 is -1. So yes, our charges count, or our signs count here, because that's going to tell us if it's a positive or a negative formal charge. Before we go into the specifics of, which one is better, which formal charge is better, how do we make the better structure, let's first just practice drawing the structures out and determining their formal charge. So if I were to take this structure here and I were to write it out, let's say we're in our ALEKS homework and it says write out this molecule, its Lewis structure, and then show its formal charge. Well, we would draw it as oxygen, double bonded to oxygen, single bonded to oxygen. This first oxygen has 1, 2, 3, 4 electrons. Middle has 2, and this last one has 3 pairs. We need to write our formal charge on the specific atom if it's something other than 0. So this first oxygen, the first one we did, had a formal charge of 0, so we write nothing on it. The middle oxygen we determined to have a formal charge of +1, so I would write a positive up around it. It can either be on the top, it can be on the bottom. I'm going to get rid of these lines because they look like minuses, okay? But we would associate that positive with that oxygen, okay? And then for that last oxygen on the end, we determined it to have a formal charge of -1, so we would put that minus right on there. There's no need to write a 1 when it's +1 or -1, similar to how we write our ion charges or anything with a 1 subscript or in a balanced reaction. Just writing plus or minus, we then assume it is 1. If the formal charge ended up being 2 or 3 or something, then you would write something like -3. This doesn't have a formal charge of -3, so we don't need to write that, but just to show you that you would then write the charge and the number next to it if it's something other than 1. Okay, so what I want you to do is I want you to draw the structures of NF3 and ClO3- using your Lewis structure rules that we talked about back in class. Okay, I want you to draw those structures, and now I want you to determine the formal charge of each of those individual atoms. Okay, so the nitrogen, the fluorines for that first structure, then the chlorines, and then the oxygens, or the chlorine and the oxygens for that second structure. Okay, so take some time, pause your video, draw those structures out in your packet, and then start assigning those formal charges and come back to me to check your work. Okay, let's focus on these structures. I'm not going to take the time to describe how I'm drawing the Lewis structures, as we did that in class. If you need some time to review that, feel free to go back through my videos to review those rules. So let's see, NF3 has a Lewis structure like that. And then ClO3-, make sure you accounted for that extra negative when you were counting those valence. So if you're missing an electron, it's probably because of that charge. Looks a little like this. This structure should not have any double bonds, even though we know oxygen likes to have double bonds or 2 bonds to it. There's no need to move any of those electrons around to get to octets, and that's the only time we form any double bonds. Okay, so make sure there are no double bonds in that structure. The key part to formal charge is having the right structure. If our structure isn't right, then our associated electrons are not going to be correct, and our formal charge will not be correct. Okay, let's look at NF3 first. So, NF3, we're going to do each individual atom. I forgot my lone pairs on my fluorines. Oopsies. Let's put those in. So, if you notice, all 3 of these fluorines look the exact same, meaning they have the same number of associated electrons. They each have 3 lone pairs and 1 bond. So all we really need to do is calculate the formal charge for one of them, and then that formal charge is going to be the same for each of them because they each have 1 bond and 3 lone pairs. So you can shorten your work by looking for atoms that look the exact same, and you'll start to see these trends in the formal charge. So let's do nitrogen first. I'm going to write this all over. So nitrogen has 5 valence electrons. And what we're going to do is we're going to subtract from that 5 valence the associated. So I'm going to write those in parentheses. So my associated electrons are going to be my lone pair electrons and then half of my bonded electrons. So in my nitrogen, I have 2 lone pair electrons, so 2 non-shared electrons. And I'm going to add to that my number of bonded electrons divided by 2. So this nitrogen has 1, 2, 3, 4, 5, 6 electrons that are wrapped up in bonds that are associated with it. So 6 that are bonded electrons, and we're going to divide that by 2. So 6 divided by 2 is 3. 2 plus 3 is 5. So we get 5 valence electrons minus 5 associated electrons. So that gives me a formal charge of 0. Okay, so my formal charge on my nitrogen is going to be 0. I am going to write it just to show that we did it. Okay, you would not typically write it on that nitrogen, but we are going to write it just to show that we did it and that it has a formal charge of 0. Okay, now let's look at the fluorine. We're only going to do one of these, so I'll put it right over here because all of them are going to have the same formal charge. We'll switch to red to do that. So, fluorine has 7 valence electrons, and we're going to subtract from that its associated. So it has 2, 4, 6 electrons in lone pairs. And we're going to add to that the number of electrons that are in bonds. So 1, 2 electrons in bonds divided by 2. So 6 plus 2 over 2, that's 1. So 6 plus 1 is 7. 7 valence minus 7 associated, that gets us to a formal charge of 0 as well. So each of these fluorines has a formal charge of 0. Now, as I said earlier, the formal charges of each of these atoms needs to add up to the total charge of the compound. Well, NF3 is neutral. It has a neutral charge, so its charge is 0. So I have 0 plus 0 plus 0 plus 0. That equals 0, so my charge equals 0 as well. Now let's look at ClO3-. So we are going to end up with a charge in this example. So let's look at the chlorine first. I'm going to put it up here in red so it differs from the blue. So chlorine also has 7 valence electrons, and we're going to subtract from that its associated. So lone pair-wise, it has 2 electrons that are in lone pairs. We're going to add to that the number of electrons that are shared in bonds, and we're going to divide it by 2. So 1, 2, 3, 4, 5, 6. 6 divided by 2. So 2 plus 6 over 2, that's 5. So we have 7 valence minus 5 associated. That gives me a formal charge of minus 2. I'm sorry, plus 2. Goodness. That's going to be 7 minus 5. That's plus 2. So it has a formal charge of plus 2. I'll rewrite this with all of its formal charges at the very end. Okay, but we did that one. Now let's look at our oxygens. All of these oxygens look the exact same. They all have 6 lone pair electrons and 1 bond. Okay, so we only have to do one of them. Oxygen has 6 valence electrons, and we need to now calculate the associated. The oxygens have 1, 2, 3 lone pairs. That corresponds to 6 electrons that are in lone pairs. We're going to add to that the total number of electrons that are in bonds and divide it by 2. So that's 1, 2 electrons that are in bonds. Divide that by 2. So that's 1. So we get 6 valence minus, 6 plus 1 is 7. 7 associated, and that gives us a formal charge of minus 1. Okay, you'll notice that these structures look very similar. The central atom has 3 bonds, 1 lone pair. The peripheral atoms all have 1 bond and 3 lone pairs, but even though they look the same, their formal charges are completely different. So if we were to redraw this structure with its formal charges, we would have Cl, oxygens, oxygen here, and oxygen there. So we decided that our chlorine had a plus 2, so put that plus 2 with that chlorine, and then each of these oxygens has a minus 1 formal charge that I'm associating with that. So our ClO3- has a total charge of minus 1. So if we add up all of these formal charges for each individual element, we are going to get that it equals minus 1. So plus 2 minus 1 minus 1 minus 1 is equal to minus 1. Essentially, these two cancel out with those 2 negative 1s, and we're left with negative 1. So it's a good way to check our work to make sure that we did our formal charge properly, that all of those formal charges now add up to the same charge. So let's keep practicing this. Let's look at some from our ALEKS homeworks. Okay, I have 2 practice problems here that I want you to try on your own, just to see where you're at. Okay, so we have N2O and NO2+. So they have the structures drawn. What I want you to do is assign the formal charge for each atom in this student's Lewis structure. Okay, so pause your video, take a second, start calculating the individual formal charges for each of these atoms. Remember, I want to see all of your work, all of those numbers done out. You can't just write the number, the final number that we get when we practice it together. Okay, show me all of that work. Okay, let's come back together and practice this, and let's see if your answers match mine. So let's look at this first one, N2O. I'm going to try to write it as small as possible. Oops. Let's do this first nitrogen. Nitrogen has 5 valence electrons. I'm going to subtract my associated. I have 2 lone pair electrons, 1, 2, 3, 4, 5, 6. Bonded electrons divided by 2. So we get 5 minus 5 is equal to 0. So that nitrogen has a formal charge of 0. Let's look to this oxygen. Oxygen has 6 valence electrons, and we're going to subtract from that the associated. There are no lone pairs on that oxygen, which I know it does not like, but it's okay, that's how the structure is drawn. So there's 0 lone pairs, which means all of these electrons are associated into bonds. So there's 8 electrons in bonds, and we're going to divide that by 2 because it only claims half. So this gives me a formal charge of plus 2. Finally, we can do this last nitrogen. Nitrogen has 5 valence electrons. Let's subtract our associated. Let's see, I have 1, 2, 3, 4, 5, 6 electrons in lone pairs, and I have 2 electrons that are in bonds. You divide that by 2. So let's see, that ends up being 7 associated, so 5 minus 7 is minus 2. So we would say that this oxygen has a plus 2, and the nitrogen has a minus 2. This nitrogen, that other nitrogen has a 0, so we don't show its formal charge. But if I add all those formal charges together, I get a neutral, which my molecule is. It does not have a charge. Now let's look to this NO2 plus. We should end up with a plus 1 for our formal charge. This first oxygen, 6 valence electrons, minus the 2 electrons that are in lone pairs, 6 electrons in bonds divided by 2, giving me a formal charge of plus 1. That's 6 minus 5. This second oxygen here, I have 6 valence electrons, minus, let's see, 0 lone pairs, and 8 paired up divided by 2. So we get a plus 2 again. And now this final nitrogen, 5 valence electrons, and let's see, 6 in lone pairs, 2 that are in bonds divided by 2, for a formal charge of minus 2. So we have this oxygen has a plus, the middle oxygen has a plus 2, and the nitrogen has a minus 2. So minus 2 plus 1, that ends up with a charge of plus 1. So that's how we're going to show our formal charges there. Okay, our next problem is a very similar one. So what I want you to do is practice this independently and have the completed problem done when you submit to the Dropbox. So I want you to show all of your work. Find the formal charge for each of these individual atoms in this structure. Make sure that it comes to the charge overall of this ion, which should be plus 1. Okay, so I want to see all of your work so that it can get fully graded when you submit this to the Dropbox. Okay, so let's start talking about how we can use formal charge to determine the best structure overall. I'm going to bring back a structure that we talked about earlier so that we can highlight some of these rules. And that's going to be this structure over here. Let's see, we have Cl, 2 lone pairs, oxygen, oxygen, and let's see, oxygen. We determined its formal charges to be plus 2, minus 1, and minus 1. Okay, that's going to be very important here. So I'm just going to copy this structure so I have it. Okay, so when there is more than one possible Lewis structure, the best arrangement of the bonds is determined by the following guidelines. Now these are guidelines, so we want to follow them as closely as possible, as we know there's always going to be exceptions to these rules. So a preferred structure is where we have a formal charge on each atom that are 0. So our NF4 or NF3 that we showed earlier had all formal charges of 0 on each of those atoms. So that would be the perfect Lewis structure because each formal charge is 0. We also want to have small formal charges. So if we're able to get formal charges to be 0 by moving electrons around, moving those lone pairs around so that we have a different number of associated electrons with that specific atom, then that is also preferred. We don't like to see large formal charges. Okay, we don't like to see the plus and minus 2s and the plus and minus 3s specifically on one individual atom. If they're spread out amongst the atoms and we have low formal charges on all of them, that's okay. But we don't want to have one individual atom with a really high formal charge, whether that's plus 2, plus 3, minus 2, minus 3. Okay, we prefer 0s and 1s. The last guideline is that formal charges should be similar to the electronegativities. Okay, they should be in line with the electronegativities. Meaning, in one structure, the more electronegative atom should have the more negative formal charge. So, if there's the ability to have an electronegative atom have a minus formal charge, then that's going to be preferred, okay? As long as there's no other way to get those formal charges down to 0. Okay, so for ClO3-, we know we're going to have a negative charge somewhere. We want that negative charge to be on the more electronegative atom. Okay, so let's use this structure to show these rules off, because the best way to learn these rules is to show them. So what I'm going to do is I'm going to start changing this structure. I'm going to start moving electrons around and then recalculating my formal charge. The way we're going to do that is step by step. I'm just going to move one lone pair at a time to see how that changes the formal charge. So what I'm going to do is I'm going to take this first structure and I'm going to take one of these lone pairs, okay, and I'm going to move it over onto the chlorine. I'm going to make it into a bond. Now chlorine can have an expanded octet, so that's fine that we're doing it that way. Okay, so what this does, is it changes our structure. So I'm going to make this change here. I'm going to change this formal charge. And it's going to look like this. So that's all I did, was I just changed one bond by moving one lone pair. But by moving one lone pair, that changes my number of associated electrons. And if I change my number of associated electrons, it's going to change my formal charge. Okay, so it actually changes the one of the oxygen and the chlorine. So if we were to recalculate this oxygen, it's still a 6 valence, but now it has 4 electrons in lone pairs and 4 electrons in bonds. So if I take those 4 bonded electrons divided by 2, I'm going to get a formal charge of 0. Okay, so this oxygen now has a formal charge of 0. That is more preferred than it having a formal charge of -1. So that is our first rule, is we would want to have a formal charge that is 0. If we can get to it where every charge is 0, then that's going to be good, but this is one step further towards getting it to 0. It also follows our second guideline that we want to have the smaller formal charge. So I went from -1 to 0. That 0 is preferred because it's smaller of a formal charge. Okay. We also have to recalculate that of chlorine because it does change the formal charge of chlorine. So let's see, 7 valence, and then its associated is now 2 lone pairs, 8 bonded divided by 2. So this gives a formal charge of +1. Okay, so even there we changed it. It went from a +2 to a +1. So again, I'm getting to that smaller formal charge. I'm avoiding that +2. So right away, we have already found a structure that's even better than before. Okay, so we went from here to here, and we got significantly better in our structure. Now what we're going to do is we're going to keep moving these lone pairs. So I'm going to take my next oxygen, and I'm going to move those lone pairs. I'm not going to choose this one because it already has a formal charge of 0. It is happy. Okay, so we don't want to do that. Okay, so if I were to move that bond, let me paste this again so you can see it. And let's redraw some of these bonds. So I'm going to get rid of one of these lone pairs. I'm going to change my structure a little bit. So we have a double bond here. I'm now going to have a double bond to my chlorine, and that's okay. This oxygen has a 0 for its formal charge. Because I added that lone pair as a bond now, the chlorine is going to change its formal charge yet again. Okay? So this oxygen now has a formal charge of 0 for the same reason we saw before. 6 valence electrons, 4 lone pairs, 4 electrons in bonded pairs divided by 2. And that gives you a formal charge of 0. So I'm again going from -1 to 0, and that's preferred. Let's recalculate chlorine. Chlorine now has 7 valence electrons, and we're going to subtract from that, let's see, it still has the 2 lone pairs, but now it has 10 electrons that are in bonds. We're going to divide that by 2. So that's 7 minus 7. This chlorine now has a formal charge of 0. Wow, we got 3 of those down to 0 now. So let's look at our structure now. I have a formal charge of 0, 0, and 0. This other oxygen has a -1 charge. This oxygen, having that -1 charge, is following its electronegativity. Oxygen is more electronegative than chlorine. If you look at those electronegativity charts we worked on in class, oxygen is more electronegative than chlorine is. So what that means is it's pulling the electrons towards itself, which is represented by this -1 formal charge. So technically, because I've minimized my formal charges on these other atoms, and my more electronegative atom has a -1 on it, it's the more negative formal charge, this is our preferred structure of ClO3-. You could go one step further to prove this to yourself and draw your structure of Cl double bond O, double bond O, double bond O. If you went that one step further by moving the lone pair again, that would put a formal charge of 0 on all of these oxygens because now they all look the same. And what it does is it puts that -1 charge that we would expect for ClO3-, it puts it onto the chlorine. Chlorine does not want those electrons. It is not the electronegative atom. So this is not the preferred structure because oxygen is more electronegative. So it's going to pull those electrons towards itself. Okay? So when we're writing our Lewis structures and we're realizing that there could be even more structures depending on moving electrons around to make double bonds or triple bonds. We usually don't see triple bonds in these cases, but more so double bonds, okay? What we're going to see is that we can move these electrons around and change that formal charge, and these are the rules that we need to follow in order to do that. So for our next practice problem, I want to bring back this carbon dioxide example that I started with. And I want you to pause your videos and I want you to determine the best structure for CO2. So between you and your neighbor, you have these two Lewis structures. I want you to say, well, this one is better because of this reason, because of the formal charge. So calculate the formal charge for each of these individual atoms, and based on those guidelines that we talked about on the previous slide, decide which one is the better structure for CO2. So pause your videos, find those formal charges, and determine the best structure. Okay, let's come back together and figure out which one is preferred. So, I'm going to do the carbon and the oxygen. Both oxygens are going to have the same formal charge because they look the same. So this carbon has 4 valence electrons minus its associated, no lone pairs, and 8 electrons in bonds. So that gives it a formal charge of 0. This oxygen, which looks like the other one, we have 6 valence electrons minus its associated, 4 electrons in lone pairs, plus 4 electrons that are in bonds divided by 2. So that gives it a formal charge of 0. So all of those atoms have a formal charge of 0. Ooh, that looks really nice, doesn't it? Having all those formal charges be 0. Okay. Let's look to the other one to just see maybe that if that one could get any better. I don't know if we can, but let's see if it could. So let's see, this carbon is going to keep the same formal charge as before because it still has no lone pairs and 4 bonds to it, so I don't need to recalculate that. Okay, this oxygen, 6 valence electrons, 2 lone pairs and 2 electrons in lone pairs and 6 electrons in bonds. So that gives it a formal charge of +1. And then this oxygen, we have 6 valence, 6 electrons in lone pairs, 2 electrons in bonds divided by 2 for a formal charge of -1. So right off the bat, those formal charges are not all 0, so not preferred. Plus, we have a +1 on the more electronegative atom. Okay, even though there's 2 oxygens, this one, yes, it's negative. That follows that third rule. This oxygen here technically follows that third rule where the minus is on the more electronegative atom. But on the opposite side, I have +1, and that's not preferred. And if there's a way to have all zeros, that is our goal. So that those guidelines are kind of like a hierarchy. So our preferred structure is going to be this first one. And you'll notice, hopefully you've been noticing throughout this lecture, that for each atom that's following those rules that we talked about, so oxygen likes to bond twice and have 2 lone pairs, carbon likes to have 4 bonds, that's when I have these formal charges that are 0, because that's when it's happiest. A formal charge of 0 is like, I'm neutral, I'm happy, do whatever you want with this structure. Okay, so here I have carbon with 4 bonds, no lone pairs, formal charge of 0. Oxygen, 2 bonds, 2 lone pairs, that's what it prefers, formal charge of 0. So you're going to start noticing those trends that as you see atoms that are following our preferred number of bonds and lone pairs, their formal charge is 0. Okay, let's do that again. So what we want to do for this next problem is we want to finish these Lewis structures, okay? And then we want to decide which one is the better choice of structures. Both are valid structures in terms of the octet rule, but which one is the better structure? So this first one, we need to finish it off by doing our octet rule. I'm missing some electrons here. So let's see, I need to have a double bond between my carbon and my oxygen. I have some lone pairs on my carbon and some lone pairs on my oxygen. Again, if you need to review going through the Lewis structures to figure out how these finish up, please go back through your notes from class. And then this second one, we need a double bond for that oxygen. Some lone pairs over here. So before you go and calculate these formal charges, just think about the structures. Which one is showing more of those trends in atoms that we saw? So carbon having 4 bonds, no lone pairs. Oxygen having 2 bonds and 2 lone pairs. Hydrogen having just 1 bond. Things like that. Think of those rules first. Based on that, which one do you think is the preferred structure? Now, I want you to prove it. So find the formal charges for each of these individual atoms, show whether they're pluses or minuses, and following those guidelines to then determine which one is the better structure. Okay. So hopefully you calculated that your hydrogens here are 0 on all of these. They all have their 1 bond. Okay, so 1 valence electron, 2 electrons in bonds divided by 2, so 1 minus 1 is 0. This carbon here on this first one in A has a formal charge of -1, and the oxygen over here has a formal charge of +1. Over here in B, carbon has a formal charge of 0, and oxygen has a formal charge of 0. So B is our preferred structure because all of those formal charges are 0. A, I have this positive on this oxygen. It's not more electronegative. carbon has that negative and it's not more electronegative than oxygen is, so it does not want to have that negative. So B is our preferred structure. Okay, so now what I want you to do is go into this last practice problem. And what I want you to do is I want you to draw the Lewis structure for each of these atoms, okay? And I want you to find the formal charge for each of those atoms. For some of these, specifically SCN and SO32 minus, or SCN minus and SO32 minus, what I want you to do is play around with the structure. Based on what you draw first, could you rearrange those electrons in order to draw out a better structure that has a better formal charge to it, following the guidelines that we talked about? I just want to point out two small typos. In your packet, yours says maximizes. I want to rewrite that as minimizes formal charge. We want the formal charge to be as small as possible. I apologize for that typo. And my other typo is this is going to be SO32 minus. Your packet says SO3 minus. It's forgetting that too. So please correct that in your packet as well. So for these, I want you to draw the Lewis structure and write the formal charge. But for the first two, I want you to draw your structure, find the formal charge, and then see if you can draw another version of that structure by moving electrons around, and then decide which one is the preferred structure based on the guidelines we just talked about. Let's talk about the second two first, just because they're not going to have variable structures because their formal charges are what they are. They follow all of our guidelines. So we have S2, 2 minus. So that structure is going to look like S, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Each S is going to have, let's see, 6 valence electrons minus 6 lone pairs, 2 electrons in bonds divided by 2. So that is going to be 6 minus 7. So they each have a formal charge of minus 1. Their structure is the same, their setup is the same. They're 1 bond, 6 lone pairs, so their formal charge is going to be the same. If we add those two numbers up, we get that 2 minus charge as we would expect. Let's look at Br F2 plus. So we have, let's see, Br in the center, 2 Fs on either side. Let's see, my F is 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 1, 2, 3, 4, 5, 6. Those lone pairs kind of look funky, but that's okay. We showed this a little bit before, but fluorine, when it has 1 bond and 6 lone pair electrons, we have, let's see, 7 valence minus 6 plus 2 over 2. So a formal charge of 0. We showed that earlier, so 0 and 0. And then for our bromine, I have 7 valence electrons. I have 4 lone pair electrons. Plus, let's see, 4 that are in bonds divided by 2. So that gets me a formal charge of plus 1. So the bromine has that plus 1. It's less electronegative than the fluorine, so the fluorine would prefer to have the 0 over that plus 1. Okay, it's not going to have a minus 1 at any point. None of these lone pairs are going to move over to make a double bond, nor would one of these lone pairs move over because fluorine cannot have an expanded octet. So that is the structure for Br F2+. So let's look at SCN minus. So you may have come up with a Lewis structure that looks like this. S, single bond C, triple bond N, lone pair, 1, 2, 3, 4, 5, 6. You could have come up with one that looks like that, or you could have come up with one that looks like this. Both of those would have happened depending on when you went to make the octet rule for carbon, where you took your lone pairs from. Okay, which ones did you move? Did you move them from sulfur, from nitrogen, from one or the other, or from both? Okay, so you could have ended up with either two structure. So let's determine which one is better. Well, each of these carbons is going to have a formal charge of 0, as we saw in our previous examples. That's how it wants its formal charge when it has 4 bonds and no lone pairs. We already calculated that. Okay. For our sulfur here, let's see if we can fit this in. I have 6 valence electrons minus 6 lone pair, 2/2 for 7. So that's going to give it a formal charge of -1. The nitrogen over here has 5 valence electrons, 2 electrons in lone pairs, 6 electrons in bonds divided by 2 for a formal charge of 0. So it has a formal charge of 0. Now the numbers work out where if I add them up together I get -1, but this negative here is not on the more electronegative atom. Nitrogen is more electronegative than the sulfur. So sulfur does not want to have that negative. The nitrogen does prefer to have the negative. So let's see if our other structure allows us to put that negative on the nitrogen. So here, sulfur, I have 6 valence, 4 lone pairs. Oops, sorry, that should be a 4/2, 4/2. For a formal charge of 0. And then my nitrogen has 5 valence, 4 electrons in lone pairs, 4 electrons in bonds divided by 2 for a formal charge of -1. So that puts that -1 on the more electronegative atom. It is more negative, so it wants to have the negative. I still have my 0 and my 0 working out. Everything else is minimized. So this is actually our preferred structure of SCN- because of the formal charge. Okay, now let's look at SO3 2-. So your first structure that you may have come up with is one that looks like this. And then some lone pairs on the sulfur. Okay. We saw before that when I have oxygen bound once with 3 lone pairs, that's a -1 formal charge. It's because they have 6 valence electrons, 6 electrons in lone pairs, 2 electrons in bonds, leading to a -1 charge. So all of those oxygens have -1s for their formal charges. The sulfur over here has a formal charge. Let's calculate it. 6 minus 2 lone pairs, 6 electrons in bonds, a +1. So it has a +1 for its formal charge there. Now, there are ways that we could move around our electrons so that we have formal charges on some of these atoms that is 0, okay? And that's what's preferred. So you're going to do like we did with the ClO3-, and you're going to take one of these oxygens, lone pairs, and you're going to make it a bond. Sulfur has the ability to be an expanded octet, so it is fine having more than 8 electrons around it. So what does this turn our structure into? S, double bond O, single bond O, single bond O. You could have chosen any of those oxygens to make this double bond. It'll all work out the same way, I promise. Okay? So these oxygens still have that -1 and the -1. But what this did was it made the other oxygen where you formed the double bond have a formal charge of 0, as we've seen with our previous examples. 6 valence, 4 lone pairs, 4 electrons in bonds divided by 2 for a formal charge of 0. So right off the bat, this is a better structure because I have a formal charge that is 0. My sulfur also changed its formal charge because it added a bond. So 6 valence, 2 lone pairs, but now it has 8 electrons that are in bonds. And that also gives it a formal charge of 0. This is our preferred structure because I have formal charges that are 0, and then the atoms that do have formal charges of -1 and -1, that -1 is going to be low. I can't have all of these have formal charges of 0 because it's a charged molecule. So the fact that each of those have -1s, that's still a small enough formal charge that it's fine. And they're on the more electronegative atom. Oxygens are more electronegative than the sulfur, so it wants to have those negatives. It's pulling the electrons towards itself. Okay, so you always want to double check, could this structure get better? Could the formal charge improve? That completes this lesson, so finish up any drawings and any calculations you may need before you submit to the Dropbox.